Are we ready to talk about the Newton's law of cooling? Are we ready? This word problem, what is it talking about cooling? I don't know. What's the word problem they're talking about cooling down? Hey, please close your Chromebook. What is it talking about cooling down on page 604? It says stew. They're talking about cooling some stew down. Now, I don't really think a bunch of chefs are in the kitchen doing Newton's law of cooling. Oh, sorry. I don't really think there's a bunch of chefs in the kitchen doing Newton's law of cooling to figure out when their stew's gonna cool down. But I'm gonna give you guys a minute, unless anybody can think of something right away. Which sciences, or if it's not chefs, who do you think really does use Newton's law of cooling? Health inspector? A health inspector?
Yeah, because they have to see how long the food can stay out before it's uneatable.
True. They probably do know scientifically an exact number. True. I need to know. I need some more ideas. The science working with food. Who's studying how quickly liquids can cool off? Who's using a formula? Because they want to know to a T, to a science, to a decimal, how long it takes for a liquid to cool down. In chemistry, maybe there's some sort of a chemical that they need to cool before they can combine. Okay. Dennis? Yes. 2 years? Yeah. Were you born here today? Okay. One thing that used to be more common, I don't feel like it's an issue anymore with cars, but we always used to have to buy coolant at the gas station to cool down our cars because our radiators weren't working. Has anybody ever seen coolant before in the gas station? I believe it's that bright green liquid. Yes, and so an engine runs about 200 degrees Fahrenheit. It gets really hot. So if they put water in there to run the radiator through, that water will boil and evaporate instantly. So instead, they run what's called coolant through it, and that coolant's a thick liquid, and its boiling point is much higher than water, so it stays cooler longer. Anyway, mechanics, engineers, the people designing the cars, they're probably using this formula a lot to make sure their cars aren't getting too hot as they're operating. All of the rocket ships, the people watching satellites, figuring out how hot that machinery is getting, are probably using Newton's law of cooling quite a bit to make sure that the machinery is not getting too hot and problem solve the heat that comes from kinetic energy. So while I think this is a cute little example about stew, I think it's more applied to machinery, right? Though, has anybody heard of the big lawsuit against McDonald's when the lady got scalded from the coffee?
Oh, yeah.
Well, no, that is what it feels like when you hear about it, but I actually think that the machine, they were trying to make this industrial coffee maker that makes coffee really quickly, it comes out hot, and they were disregarding what the human body can actually handle, and it was really actually coming out scalding hot.
But I feel like every time you get hot, you should predict that coffee's going to be hot. Every time you get coffee, I feel like it's always too hot.
You should also predict if someone's serving you food that you'll be able to consume it.
Yeah, but
I think she was like really burnt. Yeah. No, but I mean, do you think it's possible to create a machine with intentions of making coffee and the water comes out at 200 degrees?
Make 200 degrees. No one's gonna do anything with their machines. They can't even get their ice cream machine working half the time.
I think, I mean, that is true, but I think there's more of a monetary. Yeah, yeah, maybe that's it. Anyway, I think that legitimately they were actually using a piece of equipment that was making like an unreasonably hot coffee in an effort to be really efficient. But I guess we don't know what they weren't doing. No. That was decades ago. They've actually now it's right where it should be. I mean, now it just takes a minute or two, and then you can drink your coffee. I think. The point was the types of burns this person got was outside the realm of what should have been served.
Wait, they got burnt in their mouth or like on their skin?
I don't know. I don't know.
You need to unpack this story.
Okay. Anyway, let's look at the stew here. All right. Well, let's break this formula down so we know exactly how to plug in. T little zero. Of course, mine's blurry. Let's see if I can get it unblurry. I did it. Okay, T little zero is the initial temperature. So I'm curious how hot coffee makers brew. What's T sub R, y'all? The room temp, the surrounding temps. Good. This has an E in it because the cooling process is continuous. It's not like every minute the liquid jumps 1 degree lower. Every second it's a little bit cooler, and that's why E or natural log is called the natural logarithm, because that increase or decrease continuous is something that is really found in nature. R is our rate. For this stew, the rate I think is negative 0.046. So the stew is cooling 4% every minute. And then the big T at the end is our goal temperature. All right, let's see if we can plug into this formula that Newton came up with and actually use it. All right, so this says that if this stew is at 212 degrees, does that sound right? Does the stew cook at 212 degrees? I don't know. I know the back of the chicken nugget package says you have to get those at least to 165 degrees. Do you know why it says that?
To defrost it.
At 164, there's a bacteria that's living. At 165, that bacteria dies and we can consume it. So it has to do with salmonella and the type of bacteria in there. So this stew, all those little sauces and spices are coming together about 212 degrees.
Miss Baldwin, I don't mean to interrupt, but your son is at the door.
Wait. All right, so the temperature is 70. How long until this stew is 100 degrees? Is 100 degrees going to be a comfortable temperature for us to eat our soup? How hot's the mouth? How hot's the human mouth? 98.7, 98.9. So 100 degrees is going to feel a little bit warm. That's going to feel like we wouldn't want it less than 98. Less than 98 is a cool drink. We want something higher than 98, not scalding. So your goal for your soup is 100. All right, here's the problem we're going to do. How long will it take to cool a stew to 100 if the room temperature is 75? Is that what it is?
Yeah.
You put your oven at 400. Oh. No, the temperature of the nugget. No.
Could be something worse.
Yeah, some airplanes
The setting.
She don't mean the obvious. No, she don't.
The week before.
Guaranteed. I'm gonna be 375. At least.
I burnt myself making it.
Right. 400 be feeling like all 400. That's real love.
Plug in your numbers in the right spots. Try it out. It's love cooling. Try it out.
My thing is, I know we're going 90% today. I might not want to put 90%.
No, the temperature is usually about 400 for shark feed, and the internal temperature has to get up to 165. Glad you cleared that up. Okay, here we go. You know your chicken nugget time. That's good. Oh yeah.
I'm sorry, make sure you're not that Literally.
Hey, we want our soup 100 degrees, a nice comfortable 100 degrees. It's starting at 212 degrees. It's a good simmer. The flavors are working. Our room is 75 degrees. It's a continual decrease of 4.6% each minute. How many minutes is it going to take for our soup to cool? Alright, so I'll go ahead. I'm going to do the parentheses. 212 minus 75, 137. My next move, subtract that 75.
So sorry.
The natural E, such an awesome application of it. It's something really continuously cooling in the air. Now I'm going to divide 137. Now, as a fraction, 25 over 137 is going to be more accurate than a decimal. So I'd like to keep that, but I'm going to write my decimal down just so everybody knows they're on the same page. Everybody who's... It's actually times T. And T is the number of minutes that go by. Okay, so when I divide this, I get 0.182. I'm actually storing the whole decimal here. Just writing that down so that you guys feel like you're on the right page. Base E, that's 2.71, but it's a number in my calculator. Here I am. Now I'm going to have to use something besides opposite, subtracting, dividing, basic stuff. Carson, do you remember how to solve it from here? The natural log of both sides. So right now it's base E. So if I want to do log E of both sides, that's like natural log of both sides. So I'm going to write log E on the left. And I'm going to write log E on the right. Now, as a reminder, log E is the same as ln. LN is the calculator button. So when I go to put Lucky in my calculator, I use the LN button. This cancels. And this is the natural log of 0.182 is approximately negative 0.046 times t. Divide. And then I'm ready to use my calculator. Pretty sure I put this little formula on the test last year. A lot of different formulas we've looked at. A lot of great applications in this chapter. Oh wow, that number came out way different. 37 is approximately t. It will take 37 minutes for the stew to cool. I wish it was a chili instead of a stew. I do try to eat chili ready before it's cooled off. Should grab my calculator next time and be like, okay, I just need to wait 8 more minutes. It'd be 110 degrees in 8 more minutes, so I'll just burn my mouth a little bit. I bet on an industrial corporate level, there are people in the big kitchens doing this formula. Because they know exactly how hot, like especially if they're using microwaves. Microwaves get food too hot. They know how long it's gonna take to cool. Oh, the heat lamp.
So health inspectors have to calculate how long it would take that food to like pathogens to grow on it.
Right, to get down to a temperature where the bacteria can grow.
Like at a certain point, yes.
And so the health inspectors are walking around with a timer. Yeah. All right, guys, let's check these questions from Friday. Number 30 was the challenge question. Number 30 was extremely difficult, I would say. This was page 610. Number 20 through 32 even.